Okay, cool. So we're starting chapter 4. This is not on the first exam, but still important. It will be on the second exam. So we're going to start with Newton's laws, and this is sort of a new topic. We're going to move to force and interaction. We'll talk about Newton's first law and then Newton's second law. We'll take a little side detour to talk about gravitational force because that turns out to be very important, and then we'll talk about Newton's third law, okay? And just as a reminder, we've spent a lot of time on kinematics. The key stuff in kinematics is just motion. So all the kinematics equations describe how things move in space. We should now be fairly we should intimately understand vectors at this point, okay? And it's still a work in progress. We're going to be using them a lot in forces as well. Kinematics is just describing motion. Dynamics is why things move. So we've talked about how things move and what they do. Now we're going to talk about why they move, okay? So anytime you have an acceleration, it comes from a force, is the spoiler. So yeah, kinematics equations describe how an object moves. Now we're going to focus on why. So this brings us to our first section, which is force and interaction. So we have to make, as always, we have to start with some definitions. So we'll talk about forces and some properties of forces. So a force is described as a push or a pull exerted on an object by an agent, okay? So something has to act on something else. Forces can be contact forces, meaning interaction forces because things are physically touching, but you can also have long-range forces like gravity, right? Gravity's there's nothing touching a ball as it falls. That's why it's called free fall, okay? The units of force are N for newtons. Newton was that one guy that did all the physics things way back when. He also ruined calculus for a while because you guys know who Leibniz is? So there's two notations when you take a derivative. So let's say you have a function and you want to take a derivative with respect to, let's say f of x, right? Well, let's f of t. We like t. If you want to take a derivative, the Newtonian notation is this, right? A second derivative would be this. Leibniz notation would look like this. And if you wanted to take a second derivative, it looks like this. Now, British people in a fit of patriotism really liked to use this notation, and the rest of Europe was using this one because Leibniz, I think, was German. I might be saying his name wrong too. But the nice thing about this is, as we noticed, if you have dx dt, you can, and it's equal to like x, you can do this, right? Or well, 1 over x, and then you can integrate both sides. So you can use calculus, like it's more functional as a notation. It's more annoying to write because a prime's obviously easier. But yeah, that ruined calculus in England and British Empire or whatever for a long time because they had to be patriotic and use Newton's things. So it's a fun fact about math, okay? A lot of drama in math. One of my favorite mathematicians, I forget his name, but he when he was like in his 20s, I'll look up the name, was a really sharp guy. He wrote down all the things his theories about math because he had a duel in the morning and he was killed. So we don't know what he would have provided for like the world of math, but he got in a duel over a girl and he died. So yay. Anyway, let's talk about some different forces. When it comes down to it, except for gravity, almost all the push and pull forces are actually electromagnetic forces because you know how like from chemistry, you know why things don't go through each other, right? There's all microscopic interactions, all these molecules and atoms are like stuck together with bonds and like there's like you can treat them like little springs. So if you want to get real nitty gritty, almost all forces are electromagnetic forces except for gravity that we deal with in this class, and friction is like the same thing, and we'll talk about that too. So tension, right? That comes down to the microscopic properties of ropes, but we sort of idealize it because it's the intro class. So tension force, we'll just give a definition, is exerted on an object by something like a rope, wire, or string, as long as the rope, wire, or string is taut or like fully pulled, right? Then you can just treat it as like this sort of object that doesn't have any mass and is really convenient. It generally works pretty well. Once you have things with mass, you have to do more complicated stuff, and we don't really go over that much in this class, but if you take the next level of mechanics, you have to like integrate along ropes and things like that. We're not going to do that. But a tension force just points in the direction of the rope. So if you have a rope pulling this way, you would draw the force this way. And when I'm talking about drawing forces, we draw them as vectors. They're arrows. And the direction matters, and it has to match your coordinate system, just like when we were talking about x and y coordinates for velocity, acceleration, all that stuff. So same idea. All right. A normal force is just a fancy name. It's exerted by a surface on an object. It's sort of like atoms are mostly empty space, but because they can't occupy the same space, you get this thing going on. We talk about it in chemistry. But essentially, a normal force is just perpendicular to the surface. And what that means is if I lean against, is this thing following me? I think it is. I don't think it is. Oh, yeah, it is. Okay, if you lean against the chalkboard, right, which way is the normal force from the chalkboard on my hand? Which way does it point? Yeah, it points out. What about the normal force on my foot? That points up. Okay, so you've got the idea. It's always perpendicular to the surface, always perpendicular to the contact point. And then when we talk about Newton's third laws, you'll notice if I like press my hands down on this table, the table exerts a normal force up on me, but I also exert a normal force down on the table. So you have to pay attention to which object you're referring to in order to figure out the forces on that object. Okay, that's what we mean by action on an object. Friction, we have two kinds. We have kinetic and we have static friction. Kinetic friction, and I think that's the lab we're doing this week. Kinetic friction is just when you're sliding. So if you're moving, it's kinetic friction. Static friction, you're not moving, so it's pretty easy to tell which one you're using. What gets tricky is when you have to decide when you overcome static friction and it becomes kinetic friction. We'll do a lot of problems on that. There'll probably be a test question on that. So the direction of friction, kinetic friction is really easy. If you're moving this way, friction is the other way. Okay? Kinetic friction is also constant. It doesn't matter how fast you're moving, which is very different from the friction of like a fluid, like air, like drag. Okay, drag changes as you change speed. Kinetic friction does not. Okay, it's just a constant. Static friction, it points in the opposite direction of where the motion would be if the thing started to move, which is a little bit more subtle when you're trying to draw it. So for instance, if you have something on a ramp, right, let's say I set this on here. If it's not moving, right, that means it would move this way, so the friction points that way. Do you know what I mean? And then once you get here,
it's always the opposite.
Always the opposite of where it would move. Yeah. So if I push, if I put this against the chalkboard, right? If I let go of it, it falls. If I'm applying a normal force here, right? That's pushing this into the board. Which way is the static friction force?
Up.
Up, because it would fall down. Okay, so it's sort of the opposite of hypothetical motion, assuming you could overcome the static friction. Static friction also relates to the normal force, so does kinetic friction. We'll talk about that when we get into more detail on friction. Drag force is a form of friction, but it's sort of the resistance of a fluid. And when we say fluid in physics, we mean any liquid or gas. Okay, so fluid has a definition of being anything that's basically not a solid, ignoring plasma. So drag also points in the opposite direction of motion. So when something's falling, there's drag in the opposite direction. We've been ignoring it when we talk about free fall, but it does come up occasionally. The drag force always opposes the direction of motion. Okay. We'll go into a lot more detail on electric and magnetic forces in the next semester of this class. Like, it's basically a whole class on electromagnetic forces. And you also have some experience with electromagnetic forces in chemistry. It creates bonding and things like that. Gravitational force we've already sort of brushed into as we talked about free fall. But gravitational force is just always pointed towards any other object with mass. Okay? And so This brings us to the concept of weight, which we'll talk about. It's different from mass, but it's related to mass. So we have, of course, our four fundamental forces. We talked about these on the first day. Gravity, the electromagnetic force, and then we have strong and weak nuclear forces, which we ignore. basically for the whole 3 semesters. We talk about them for like 20 minutes in the last semester of this series. But if you really want to be, like a nuclear physicist, that's important. But yeah, normally we just take this for granted. Atoms are just doing their atom things, and we don't worry about it. Okay, so let's try a question. So if you don't have a clicker, this is when you go get a clicker. And there we go. Okay, we're sort of tied between B and C. Please discuss. We'll vote again. And we have a slight shift towards C. Okay, so we've kicked a rock. I don't have any rock for demonstration, but we've kicked a rock, and now it's sliding across the floor. Okay, so what forces? Well, let's draw a picture, I guess. What forces are acting on this rock? So here's the floor. There's a rock. We know that the rock is sliding. If I were better at drawing, it'd be helpful. So the rock is sliding, so we know it has some speed. V, and here's like a foot over here. Okay, but is the foot in contact with the rock anymore? No. Okay. So what forces would you expect to be acting on the rock? Gravity, right? And so we call that force of gravity, which we'll find out later is equal to mg. Anything else?
Friction.
Friction, probably, right? So that would go this way. What kind of friction would that be? Kinetic. Anything else?
Normal force.
Normal force, pointing perpendicular. Any other forces there? No. So gravity acting downward, normal force acting upward. What about the force of the kick?
The foot's no longer in touch with the rock.
The foot's no longer in contact with the rock, so that one goes away. Friction is good. So all of these are cool except for C. That one is only a force while your foot is touching the rock. Yes?
So is kinetic friction also opposite?
Yes.
All friction?
Yes.
Not only static?
Well, it's not, well, because here's the thing. If friction points in the direction of motion, then you have an acceleration in the direction of motion, and then friction speeds things up, which doesn't make sense. So friction always has to oppose motion because friction always slows things down.
Oh, okay.
Yeah. Or makes them not move is the other option. So the difference is not, it's always in the opposite of the direction of motion, even if there is no motion. So it's either holding something in place or slowing it down.
Okay.
Yeah. Cool. So let's talk about net forces. So when we talk about acceleration is going to be proportional to the sum of the net forces. And what I mean by net forces is forces are vectors. So you figure out all the forces, like we did here, you add them all up, and then you figure out which direction the acceleration is. And then we go back to being able to do kinematics. Okay, so what we do there is, so for instance, let's say this is a sort of weird tug-of-war where people are pulling on this box, okay? And we'll only worry about motion in this plane. So like if it's sitting on the ground, if it has gravity, we're gonna just ignore that for now. But you could assume gravity would point down, normal force would point up if it's sitting on the ground. But the way we figure out the sum of all forces is you would draw your tension force here, draw your tension force there. This is our force diagram for this situation. We basically draw the box as a dot, and then you draw the force vectors in the direction of the tension, okay? If you want to figure out the net force, what do you do with these? Add them, and if we add them, they look like this. Okay, so this would be our net force. That's why we did all this vector addition earlier in the class. So